All right, so in this video, we're going to discuss our 5 reaction types, and we're going to discuss them in the simplest terms possible. So, let's get started. So, the first one is going to be the formation reaction. Our formation reaction is always talked about as an element plus an element will yield a new compound. So, element plus element equals a compound. So, when you are given any sort of equation, you need to say to yourself, what are my reactants? Are they elements? Are they compounds? Are they one of each? What are they? And then look at my products. What am I actually getting out the other side? That will always help you determine what's actually going on. So, in this case, an example of element plus element leads to compound. Let's talk about sodium, which in its natural state will be solid at room temperature, plus another element, which we'll talk about, fluorine, which will be a gas at room temperature. If you're confused about this too, we're discussing it as a gas. Fluorine is one of those elements that cannot be by itself. It is a diatomic. It needs a friend at all times. So this element plus this element, well, that's going to form an ionic compound, and that's going to give me NaF. And ionic compounds are generally solid at room temperature, and we're good to go. I'm going to balance this out. If you're confused about the balancing, please check out my balance video. So I have sodium element, fluorine element, compound, sodium fluoride. The next reaction we're going to discuss is going to just be the opposite. So our decomposition is where we start with a compound and we are reduced to element and another element. So when I look across this, I need to see, hey, what's my reactant? Oh, my reactant's a compound. What are my products? My products come out the other side. They are now elements. So just really think about what actually is going on inside of these equations at any time. So we're going to talk about the decomposition of table salt. So table salt, sodium chloride, which again at room temperature is a solid, it is an ionic, breaks up into its elements, which will be sodium, and at room temperature, chlorine. And balance that one out. And we're good to go. So there's a great start, our formation and decomposition reactions. Our next two that we're going to talk about are going to be single and double replacements. So our third one will be a single replacement. Single replacement is where you have elements plus a compound, yielding you with an element and a compound. So, a good thing to remember when we talk about single and double replacements is that they're always happening inside of the water. So we always are working with some kind of solution. So let's consider the idea that we have a, I don't know, let's go with a copper and lead, let's go with silver nitrate solution. Now, remember, nitrate is a polyatomic atom, so we keep it together. We think about it as a separate entity, and we need to get a new element. So one of these is going to have to switch. So copper needs a new home, and when he's thinking about a new home, he wants something similar to what he's used to. Copper is a metal. So it being a metal wants a metal home. It looks over here, it says, hey, silver is a metal. I'm going to take silver's home. That's where I want to be. So copper is going to come in here and kick silver out of its home and take over its spot with nitrate. So element plus compound. So my new element is going to be silver. And my new compound is going to be copper nitrate. Now it's important with these ones that we always consider our most common charges, which for copper I believe is going to be copper 2. So remember, element, compound, element, compound. The element is always trying to take the space most familiar to it. So it wants the metal's home if it's a metal. If it is a non-metal, it's going to try and take the non-metal spot in an ionic compound. If it reacts with a molecular compound, then you are going to have a little bit of a problem. You're probably not going to see a question written towards you that way. So what comes after single replacement? We're going to discuss a double replacement. So our double replacement is now going to be compound plus compound leaves me to have compound plus compound. And just like single replacements, these exist inside of water. That's how they all react with one another. So compound plus compound. Let's think about what we could possibly have react. So a double replacement that might be nice to work with will be, let's go with lead nitrate and potassium iodide. These are both going to be aqueous. Now, in the other one, we concern ourselves with which one is going to take the spot of. But with a double replacement, they're both switching spots. So regardless of whether I switch the nitrate around or the iodine around or anything crazy like that, it's largely irrelevant because you always end up with the same two products. So in this one, I would just like to follow the metals around. So I'm going to switch lead out, and that is going to give me lead iodide and potassium nitrate. Now for both of these, your balancing can be a little bit more confusing. So with this one, I need to follow along here and here. With this one, I need to make sure that I balance out my I's and I balance out my K's, and we're good to go. The last type of reaction we're going to discuss is going to be a combustion reaction. Now, combustion reactions are kind of tricky, but they don't have to be. A combustion reaction is always made up of the same 4 components. So you need something to burn, you need oxygen. So you always need oxygen. And when we're talking about hydrocarbon combustion, you'll always end up with the same 2 products, CO2 gas and water vapor. So outside of that, really, the only thing you have left to consider is what you're actually burning. In a lot of cases, you end up with a hydrocarbon. So in this case, I'm going to select methane, which burns as a gas. However, this could change out in a lot of ways, and this only changes out your balance. So when I think about methane combusting, I have carbon. Carbon, I need to have double the amount of hydrogen to match that, and then I need to match up my O2, and we're good to go. Now, this can be switched out with a lot of things, and not only carbon can burn. There's lots of other things out there that we can light on fire. A great example is sulfur. If we were to light sulfur on fire, we still need a lot of the same products. O2, but instead of CO2, I now have SO2. As far as the water is concerned, water is not produced in this particular reaction because I don't have any hydrogen in my compound. The hydrogen is always your tip-off that water could be included. So I have all of what I need for the reaction, and then it just comes down to balance. And it's as simple as that. With combustion reactions, you're always looking for some sort of oxide. If an oxide shows up, you're usually pretty good to know that it's going to be a combustion reaction. The ones that can confuse you are rusting reactions. And rusting we sometimes consider in the same category as combustion. It's just that we don't see a flame associated with it, but they do give off heat. So an example of that would be iron plus oxygen. We've seen this before. We've seen it on the sides of our bikes. And this looks drastically similar to what's going on with our combustion reaction. So sometimes we consider them to be the same thing. Again, at the end of this, we just need to balance this whole big thing out. So there we go. 2, 3, and 4 irons. And that's it. Really, when it comes down to your reactions, consider what you're working with. So for formation, you're looking for element plus element leads to compound. For decomposition, you're looking for a compound breaking up into its elements. For single replacement, you're looking for element plus compound leads to element plus compound. Be careful on single replacements that things switch the right way. For double replacements, you need to make sure that you watch solubility, but more important that you just make sure that you watch your charges, because when you switch compounds around, sometimes you don't carry charges correctly. Finally, with combustion, the big tip off with these, you always need oxygen. You need to come up with some sort of oxide, and there's always energy released. Combustion reactions can be tricky, but they are so different than everything else, they're usually easy to pick out in a crowd. Alright, make sure to check out the balancing video. Make sure that you are comfortable with your balancing as well. And that will be it. You will be a master at reactions.